Hello, we are discussing about gate video lectures on electronic devices. The topic we are discussing is diode switching times. Look at this diagram. Here the diode is given with an input signal. The input voltage is going to be suddenly changed at t is equal to t1. Before t1, diode input voltage is positive. After t1, input voltage is negative. So instantaneously at t is equal to t1, input voltage is changing from positive voltage to negative voltage. Assume that this positive voltage is sufficient enough to keep the diode is under forward bias, and just before t is equal to t1, diode has reached steady state under forward bias, and at t is equal to t1 the input signal is changed such that diode should go into reverse bias and it should reach steady state under reverse bias. So ideally the diode should switch from on to off instantaneously, but practical diode doesn't switch instantaneously, it requires some time due to the minority charge concentration stored in p and n sides. So we'll discuss these things. According to this diagram, the diode should change from forward bias to reverse bias. So first we will see about the diode under open circuit, later what is meant by steady state forward bias situation, next what is meant by steady state reverse bias situation, and how much time does it requires to switch from steady state forward bias to steady state reverse bias. This is a simple PN junction under open circuit, that is whenever no voltages are applied. This is a simple PN junction. Assume n side is heavily doped than p side, that is n type concentration, electron concentration is more than hole concentration in p type. So we can draw the electron and hole concentrations under equilibrium for open circuit condition is like this one. This is a junction. So here we neglected the depletion layer width, so that we have drawn a vertical line, and left of this vertical line is p type, right of this vertical line is n type. For p type majority carriers are holes, so it is indicating it as pp naught. Holes in p type under equilibrium, naught implies equilibrium. Nn naught, electrons in n type under equilibrium, they are majority carriers. Majority carriers drawn with red line, whereas minority carriers represented with black line. Under equilibrium condition, Np naught is electrons in p type under equilibrium, they are minority carriers in p type. Pn naught, holes in n type under equilibrium, they are minority carriers in n type. So if you are looking at this x-axis, this is simply x-axis, there is no negative x-axis. This side is also treated as positive x-axis, this side is also treated as positive x-axis. The meaning of positive x-axis is nothing but as you are moving far away from the junction on n side as well as on p side. Now if we apply forward bias for the PN junction, forward bias definition is nothing but voltage on p side must be more positive than voltage on n side. So with the help of single battery we can represent positive terminal is connecting towards p side, negative terminal is connecting towards n side, that makes more positive voltage on p side than n side. So we can say that one diode is under forward bias. Under forward bias, from this diagram we can say that one this positive terminal is going to be repelling the holes present in p type. So holes present in p type is pp naught, they are repelled by the positive terminal, so they will enter into n side. When the holes are enter into n side, they will become minority carriers. So initially at the junction they are very large in number, but as they moved into n side they will become minority carriers, and they will try to recombine with the electrons present in the n type, which are majority carriers. So the concentration of holes are very large near the junction, and as you are moving far away from the junction towards n side, the hole concentration gets reduced exponentially. Similarly, for the N side, N-side majority carriers are electrons which are repelled by the negative terminal because of forward bias, and the repelled electrons are entered into P side. Initially they will be very large in number at the junction, and as they enter into P side they will become minority carriers. They will try to recombine with the holes present in P side, which are majority carriers. So the concentration of electrons is exponentially reduces from the junction as you are moving away from the junction towards P side. So this is the diagram representing minority carrier concentration. We are not going with the PP naught and NN naught majority carriers. Here majority carriers are moving towards other side, they will become minority carriers. So we are considering those graphs. So now previously that was P naught, which are now whenever they are entering into N side, at that time they will become minority carriers. So minority carriers at N type is represented with Pn. This solid line represents Pn. So Pn is now sum of Pn naught as previous plus excess holes. That excess holes is nothing but total holes minus Pn naught. So Pn minus Pn naught is nothing but excess minority carrier charge on N side. Similarly, for N side also, for P side, these are electrons. Solid line represents minority carriers, that is electrons in P type, which is represented with Np, and that will be sum of excess minority carriers Np minus Np naught with Np naught steady state value. So this Np minus Np naught and Pn minus Pn naught is going to be called as excess minority carrier charge. Otherwise Np minus Np naught is excess electron density, or Pn minus Pn naught is excess hole density. So under equilibrium condition for forward bias, this is the concentration of minority carriers on P side and N side. So you will get a large number of minority carriers which have been injected near the junction under steady state forward bias. Now we will see what happens if you apply reverse bias for the open circuit Pn junction. This is open circuit Pn junction with the carrier concentrations represented with majority and minority carriers. Let us apply reverse bias. Reverse bias defined as more negative voltage on P side than N side, otherwise more positive voltage on N side than P side. Both will be giving the same reverse bias. During reverse bias, negative terminal is connecting towards P side, so that P side is majority carriers are holes. Holes have been attracted by this negative terminal, and electrons are majority carriers in N type. They are attracted by this positive terminal. So majority carriers from P side and N side, they are not crossing the junction, simply they are attracted by the respective terminals. So they are not forming a closed loop. Holes are attracted towards negative side, electrons are attracted towards positive side. They are not crossing the junction. I think you have observed. So since they are not crossing the junction, they are not forming the closed loop, so majority carriers doesn't contribute for the current under reverse bias. Now what happens to minority carriers? Minority carriers in P type are electrons. Electrons will be repelled by this negative terminal, so that they will cross the junction. Later they will be attracted by this positive terminal. So that now the minority carriers electrons in P type are going to be repelled by this negative terminal, and they are crossing the junction, and they are being attracted by this positive terminal. So they are forming a closed loop. Similarly, holes in N type are minority carriers which are repelled by this positive terminal. They will enter into P side, and they will attracted by this negative terminal. So minority carriers will find a loop. So minority carriers cross the junction, they will find a loop, they will contribute for the current. But minority carriers are very small in number, so that current under reverse bias is very small, nano amperes in silicon whereas microampere range in germanium. Ideally, the reverse saturation current is 0. So, minority carriers. Now we will concentrate only on minority carriers. They are contributing for the current under reverse bias. These are minority carriers NP naught. They will be crossing the junction and they are going into other side. Minority carriers holes in N type. They are going to be attracted towards other side. So near the junction they will be attracted so that there will be no charge carriers near the junction. Look at this point. Dotted line represents equilibrium values, whereas solid line represents the actual values. So this solid line represents there are no number of electrons present near the junction in p side, no number of holes present in n type, n side near the junction, as it is moving away from the junction and again it is reaching the equilibrium values. So this is the situation under steady state reverse bias. If the diode has reached this situation, we can say that one diode is completely under reverse bias. Now, if you suddenly change the voltage from forward bias to reverse bias, you must get a situation previously what we have seen under steady state forward bias, and that should change instantaneously towards this situation under steady state reverse bias, which doesn't happen instantaneously. That requires some amount of time. That time required to change from forward bias to reverse bias is called as reverse recovery time. We will discuss that reverse recovery time now. Let us assume you are applying a voltage Vf for the diode, and the input voltage we are assuming that one we are in the duration of time t less than t1. T less than t1, the input voltage is Vf. Vf is applying to this diode, so diode is under forward bias, and assume that one it is under steady state. So this is the situation results. This is a minority carrier situation. Under steady state forward bias. Now this steady state forward bias situation specifies that one it has a large number of excess minority carriers present near the junction. To go into reverse bias, first of all this excess minority charge should be removed. Later it comes into open circuit condition, and later this will be comes into the steady state reverse bias by removing the minority carriers present near the junction. So first step is nothing but removing the excess minority carriers, that is NP minus NP naught and Pn minus Pn naught. These will be removed so that it is coming into the open circuit condition, and from that one it is coming towards reverse bias steady state condition. For that one it requires a time. So during this removal time the diode is going to be conducting. During this time, since they are very large in minority carriers is very large, that is excess minority carrier charge, while it is going to be removing at that time the current due to that large number of minority carriers is going to be large enough. So the diode conducts for some duration of time until it has been removed the excess minority carrier charge. Later it requires some more time to reach the steady state reverse bias. So we can draw the waveforms in this way. Let us assume input voltage is going to be applied. Before t is equal to t1, just look at this vertical line. Left of this vertical line implies nothing but diode is under forward bias. Whenever the diode is under forward bias, excess minority carrier charge on p side, on n side, for excess minority carriers on n side is Pn minus Pn naught, and because of that one you will get a large forward bias current. That forward current is nothing but Vf by R. Okay, this is the line Vf by R is nothing but forward current, and by that time output voltage, diode voltage at that time it is going to be equal to cut-in voltage, 0.7 volts for silicon, zero point 0.2 volts for germanium. This is very small in forward bias. Look at this one. If the input voltage suddenly changes towards minus Vr at t is equal to T1, that is this line, so the first step it has to do is nothing but it should remove the excess minority carrier charge, but it requires some time. During that time the diode conducts, but in reverse direction, because it is removing previously how they have been moved, now they are moving in opposite direction, so that now you will get the large amount of current but in opposite direction, so that this diode current previously it was in positive y-axis direction, now it is showing in the negative y direction. So this is negative current which is flowing from N to P. The value of this current during this storage time, that is nothing but during the time required to remove the minority carrier charge, can be calculated using the equation as minus Vr by R. This is very very important, minus Vr by R. So storage time is the time required to remove the excess minority carrier charge, and after that one it comes into the open circuit condition. From that one reverse bias is going to be taking place, and because of that one, to reach the steady state reverse bias it requires some more time, that is nothing but transition time. So after this time, this transition time, the diode is under steady state reverse bias. So before this T1 diode is under steady state forward bias, after this T is equal to T3 the diode is under steady state reverse bias. So the time required for the diode to come from forward bias to reverse bias is nothing but sum of storage time plus transition time. So it is very very large whenever it is changing from forward bias to reverse bias, but whenever it is changing from reverse bias to forward bias it takes less time. That time is called as forward recovery time. So the sum of storage time and transition time whenever it is changing from forward to reverse, it is called as reverse recovery time, indicated with TRR. TRR is equal to TS plus TT, storage time plus transition time. We can summarize switching times in this way. Diode switching times. In AC applications, when diode is instantaneously switched from a conduction state to a non-conduction state, that is forward bias to reverse bias, it needs some time to return to non-conduction state, so behaves as short circuit for a little time period in reverse direction. This occurs because when the diode biasing is suddenly changed, the majority charge carriers migrated to other region is the minority charge carriers in that region. The time required to return back to state of non-conduction is called as reverse recovery time, which is sum of storage time and transition time. So storage time is the time period for which diode remains in conduction state even in the reverse direction. So that is the time required to remove excess minority carrier charge so that it is attaining this situation. Next, transition time is the time elapsed in returning back to the state of non-conduction. So from this state it has to come towards steady state reverse bias. For that one how much time it requires, that is called as transition time. So reverse recovery time is the time required for the diode to change from forward bias to reverse bias, whereas forward recovery time is the time required for the diode to change from reverse bias to forward bias. Generally, reverse recovery time dominates over forward recovery time. So we must study on reverse recovery time. To get more video lectures, look into www eget.ws. Thank you.